In the last video, we talked about how to deal with non-diagonalizable matrices by perturbing them and making them diagonalizable. Now, this involves a bunch of analysis. You have to take limits, you have to use L'Hopital's rule. Sometimes you don't want to do that. In this video, we're going to talk about a different approach, which is accept that they're non-diagonalizable and find vectors that behave in an appropriate way with respect to those matrices. Those vectors are called power vectors. Now, the idea of a power vector is it's a generalization of the idea of an eigenvector. See, an eigenvector is something where ax is lambda x. And so that means that a minus lambda times the identity times x equals 0. A power vector isn't killed by a minus lambda I, it's killed by a power of a minus lambda I. So if you have a vector where when you hit it with a minus lambda I, p times it dies, but if you hit it p minus 1 times it doesn't die, then we call that a power vector of degree p. Sometimes these are called generalized eigenvectors. I don't like that term. I'm going to call them power vectors. Okay? And eigenvectors are a special case of power vectors where p equals 1. A minus lambda I times x is 0, and the 0th power of a minus lambda I times x is just x. So these are a generalization of the idea of an eigenvector. So let's look at an example. The most basic example is, we've looked at 1, 1, 0, 1. We're going to look at 2, 1, 0, 2 this time. If you look at that, that's an eigenvector with eigenvalue 2. Because if you multiply, subtract off twice the identity, and you multiply by 1, 0, you get 0. Or if you prefer, if you multiply the original matrix by 1, 0, you get twice 1, 0. So this is a times a minus lambda I x is 0, or you can say ax equals lambda x. They're equivalent. This is an eigenvector. But this isn't diagonalizable. If you look at 0, 1, that's not an eigenvector. But 0, 1 is a power vector. You see, if you multiply a minus 2i times a minus 2i times 0, 1, you do the first multiplication and you get 1, 0. And then you multiply by this again and you get 0, 0. So you start with a power vector of degree 2, you hit it with a minus 2i, and you get a power vector of degree 1, in other words, an eigenvector. Hit it with a minus 2i again, you kill it. So here's another example, a little bit more subtle. Let's look at the matrix 3, 1, negative 1, 1. If you find its characteristic polynomial, it works out to lambda squared minus 4 lambda plus 4, which is lambda minus 2 squared. Has 2 as an eigenvalue, and it's a double root. You could also tell that because the trace is 4, 3 plus 1, and the determinant is 4, 3 minus negative 1. So two numbers that add up to 4 and multiply up to 4, got to be 2 and 2. Now, we can look for our eigenspace. To find our eigenspace, we look at a minus twice the identity, and we row reduce it, and we find the null space of the row reduced matrix. That gives us our equations. x1 is minus x2. x2 can be anything it wants. So we could say that our eigenvector is negative 1, 1, and I prefer to use 1, negative 1. So that's an eigenvector. But now let's look at the vector 1, 0. I claim that's a power vector of degree 2. Because let's check. If we apply a minus twice the identity to it twice, here's a minus twice the identity, you multiply it out. If you multiply it once, you get 1, negative 1, and you multiply it again, you get 0. So that's a power vector. So what's so great about power vectors? Well, these two together form a basis. These are linearly independent, and they give you a basis for R2. And let's see what the matrix looks like in that basis. You see, if you apply a to the eigenvector, you get twice the eigenvector. And if you applied a minus twice the identity to the second vector, you happen to get the first vector, which means that a applied to the second vector gave you the first vector plus twice the second vector. And now we can look at that in the B basis. A, B1, the coordinates in the B basis are 2, 0. AB2, the coordinates in the B basis are 1, 2. And we discover that if we use this basis, then this example looks just like our previous example. It's not diagonalizable. You can't make it into a diagonal matrix, but you can make it into what's the next best thing. This is called Jordan form. And we're going to see more about Jordan form in a couple of minutes. So here are what we do in general. Instead of looking at an eigenspace, E lambda, we're going to look at the power space, E lambda with a twiddle on top. And that's going to be all of the power vectors that have that eigenvalue, no matter what their degree is. And that's the same thing as the null space, but it's not the null space of A minus lambda times the identity. It's the null space of a power of A minus lambda to the identity. And it turns out that the algebraic multiplicity is big enough, is a big enough power to catch all of them. So this contains the eigenspace because all the because those are killed by one power, but it can contain more than the eigenspace. In general, all of the degrees of the power vectors, they can never be bigger than the algebraic multiplicity. And the dimension of the power space is always equal to the algebraic multiplicity. So, if the geometric multiplicity was the same as the algebraic multiplicity, then E lambda would have that dimension, and this has that dimension, so they're the same. You don't get any extra power vectors. If the geometric equals algebraic, the eigenvectors are the only thing in town. But if the geometric is smaller than the algebraic, then the eigenspace is smaller than the power space, and you need extra power vectors to give you this dimensional space. So the upshot, here's the big theorem, is that if you have any n by n matrix, whether it's diagonalizable or not, you can always find a basis consisting of power vectors. Some of them are eigenvectors, others are power vectors of degree 2, 3, 4, whatever. And if you choose the basis in exactly the right way, you can write the matrix to be block diagonal, where each block looks just like what we saw before. It had eigenvalues on the diagonals and ones above the diagonal, and this is called a Jordan block. So here are some examples of matrices in Jordan canonical form, some 3x3 matrices. If it's a diagonal matrix, then it's in Jordan canonical form. The blocks just happen to be 1x1 blocks. And here, likewise, they're 1x1 blocks. Two of them happen to have the same eigenvalue, but if you have two-dimensional eigenspace, that's actually going to give you two Jordan blocks for that eigenvalue. Now here we have a situation where we have a 1x1 block, because 1, 0, 0 is an eigenvector, and we have a 2x2 block. 0, 1, 0 is an eigenvector, 0, 0, 1 is not. It's a power vector, but not an eigenvector. Here we still have a 1x1 and a 2x2. Here you have two eigenvectors with eigenvalue 2 and a power vector with eigenvalue 2. And here you have one eigenvector with eigenvalue 2, namely 1, 0, 0, a power vector of degree 2, and a power vector of degree 3. So, diagonalizable matrices go in Jordan form, and all the blocks are 1x1 blocks. If it's not diagonalizable, then you have bigger blocks. And for each block, 1, 0, 0, 0, 0 is an eigenvector, 0, 1, 0, 0, 0, 0 is a power vector of degree 2, 0, 0, 1 is a power vector of degree 3, and so on.